Alright, so in this video, we are covering day 23 of Advent of Code, and this problem is a state evolution problem, and specifically, it's a kind of diffusion problem. Our elves start off standing in a 2D grid, and gradually they start spreading out so that they can plant some trees. And there are very particular rules that dictate how they move and how they try to spread out. So for part 1, we just want to calculate the area that they are covering at the end of 10 rounds. So we just take the largest rectangle that surrounds all of the elves' positions and we give its area. And then for part 2, we just calculate until we get to a point where no elf has moved. So we want our final stable state, because one of the rules about how the elves are moving is that if there are no elves around them, they will stand still. So if we reach a position where all of them have no neighbors, then we are finished. So let's go over some of those rules that they use to move. Generally speaking, we have a direction priority. So we will cycle through the directions north, south, west, and east. And with each different round, the priority of the directions changes. So we start off with the priority being the order I said first, north, south, west, east. And so every elf will look to its north, and it will look in all 3 directions, so north, northeast, northwest. And if there are no other elves in those positions, the elf will propose moving north 1 step. Now, if north doesn't work out, the elf will also propose moving south, again, if it is empty in those 3 directions below it. And then so on and so forth. After round 1, the priority becomes south, west, east, and north. So the elves will first propose moving south if they have a valid south move. Otherwise, they will move on in this order. So it is cyclic. And one other caveat is that if 2 elves propose moving into the same space, then neither of them moves. This can only happen coming at it from opposite directions. So if one elf tries to move north into a space and a different elf moves south into that same space, neither of them move. Same with east and west. So those are the rules we're dealing with. Let's look at our input. It's just a 2D grid. We have spaces that are occupied by the elves and spaces that are unoccupied. So that's really simple. We just parse a 2D hash map. We've done that a lot of times. If it's a period, we say false, this square is not occupied. If it's the hashtag, then it is occupied. So the product of our parsing is just a hash set of occupied coordinates. Now, let's talk about actually solving this problem. So, as I said, it's a state evolution problem, and so we need to keep track of what our state is. We will want to track the current set of occupied coordinates, and we also want to know what the current direction priority is. And a final piece of state we will track is whether or not all of the elves stood still on the previous move, because that will be our terminal condition in part 2. So I have this pattern that I've used very commonly throughout Advent of Code, solve state n. This basically says run a state evolution function n times. So for the first part, we're just doing that. It's very simple. So it's just a matter of defining this evolve state function. And I wrote everything out because there are several steps to this, but high level, we want to get all of the proposed moves from the elves. We want to exclude moves where 2 elves try to move to the same location. Then we want to update our set of occupied squares. Finally, we want to update the state by rotating the directions, and we want to determine if any elves have moved. So let's think about step 1. Step 1 is a fold. So notice we're using a fold M here, and we have 2 pieces of state that are associated with this fold. We want to have an occurrence map of the different coordinates because we want to track if 2 elves move into the same space. We'll use that in step 2. The other data we're tracking is a mapping from coordinate to coordinate. And the key of this mapping will be the proposed moves, and the value will be the previous location of that elf. The reason we're doing it this way is so that we can remove the old location of the elf from our occupied set. So that captures 1A and B. Now we need to do part C, 1C of this set of directions. We need to see which directions are empty for the elf to move in. So we can find if the north direction is empty by considering, given that the elf is standing on row column, for north we want to look at row -1, col -1, that's the northwest direction, row -1, col, that's directly north, and then row -1, col +1, that's northeast. For south, we do the same thing, just looking in the 3 south locations, east and west. All of this is very simple. So when do we stand still? We stand still if all of these are empty. That's another condition we'll have here. Now, we do want to calculate a trial move. So given the head of the set of directions we have, so directions is an input to this function, and it will be guaranteed to have a head, we can calculate the order in which we go through these trial moves. So notice I'm using the alternative syntax here. So if north is the first direction, then we try north. So what are these try functions? That's probably worth going over first. Down here, we basically say, okay, if north is not empty, if this boolean is false, then we're just going to return nothing. We can't have a trial move there. Otherwise, we return the actual coordinate that we are moving to. So in the case of north, we take row -1, south is row +1, etc., etc. So we take the Boolean value that we calculated up above and we pass that as an argument here just to determine if we get a just value or a nothing value. And so we do it in order. We try north, then south, west, and east. So if south is first, we just try south in the first position, then we try north in the last position, and we just keep rotating through them depending on what the head of our directions list is. Now, if we have a valid trial move and we are not standing still, then we are going to insert into our dictionary, or I should say our hash map. So the key, like I said, is the trial move. The value is the previous location, the one that we're standing on as we're in this function. And then we're also going to increment the key of the proposed trial move. Now, if there is no good trial move, we make no updates. Our previous moves dictionary stays the same. Our destination occurrence map stays the same. And so we just use a fold to do this for all of the current elves. So for each location currently in our elf set. Now we have to filter this set of occurrences by saying, okay, we only want the new locations where the number of occurrences is exactly 1. Because if there's 2, then we don't want to actually move anyone into that space. Okay, so now we have step 3. We want to calculate the updated set based on the proposed moves and also based on the spaces that have 1. So we're going to loop through all of the spaces that only have an occurrence value of 1, and we're going to use as a reference point this proposed moves dictionary. Let's look at this function defined down here. So we have our move lookup dictionary, we have the previous set of coordinates, and we have the new location. So what do we do first? We look up the previous location associated with our new location, and then we delete that from our previous set. So we're deleting the old location first, and then we're inserting the new location. That's what's happening here. It's just nested hash set inserts. And we use a fold. We just go through all of the spaces that are occupied or that are going to be occupied by just one single elf. And at the end of the day, we return our updated set from this function. We also want to return a rotated directions list. So what this really means is that we take the tail of the directions and just append the head of the directions at the end. Finally, the last bit of information we need from evolving the state is we just say, okay, was spaces with 1 null? So if spaces with 1 was null, this evaluates as true, and this will evaluate as false. And so that means we're not going to continue running this evolution, and we can just sort of stop. So we'll use that in part 2. But the part 1 code, all it is just running that state evolution 10 times. Our initial state, we use the hash set of the inputs, and then we have the list of directions just before in the original order, and that'll get modified over time. And then we just always set true to start off with, because once that is false, we will stop doing the state evolution. So for part 2, we don't actually have to write that much more code. We're using a slightly different state evolution mechanism. We're always doing n+1 because now we're counting up instead of down, because our end condition is not that n is equal to 0. Our end condition occurs when we hit false. So for our base case, we return n when we know that none of the elves have moved. Otherwise, we just evolve our state again, we increment our counter, and we return a recursive call that uses this updated state. That's all we need to do for this function. I'll show my answers like I have been. So for the first part, we get that the rectangle area is 110 after 10 moves and about 4,000 after 10 moves in the larger input. I guess I forgot to show that last little bit of code. We do have to calculate the size of that rectangle. It's not actually that hard. We just unzip all of our occupied squares to get the row indices and the column indices. We take the minimum of the rows, the maximum of the rows, the minimum of the columns, and the maximum of the columns to calculate the size of that rectangle. So it's just an area calculation, max minus min plus 1 in both dimensions. And we also have to subtract the size of the occupied squares. So we want the number of unoccupied squares in that area. So I guess I misspoke earlier. But then for the second part, we just want to see how many rounds it takes for us to be complete. And with smaller input, that turns out to be 20. With the larger input, it's about 900, so it actually takes a while. But I didn't find I needed any real performance tricks in this. It just sort of worked, so this was a pretty easy problem overall compared to some of the other problems we're getting at this point in the season. So hopefully this was helpful to you and you're now able to solve this video. If you are enjoying this series of videos, I encourage you to subscribe to the Monday Morning Haskell mailing list so you can stay up to date with our content. Subscribe to our YouTube channel as well. If you want to see a full write-up for this solution, you can also go to the blog. That link is in the video description as well, showing you, okay, this is in writing how I did everything. And finally, the source code for this answer is also linked there. So if you need any of those items, feel free to follow those links. Thank you so much for watching, and I'll be back soon with day 24.